For exercise 326, it's asking for each pair of compounds below, predict which will be more acidic. So which one of these is more likely to give away the hydrogen? Okay, well, in this first one, the hydrogen is bonded to a chlorine. Always consider the atom first. That's the most important of our 4 qualitative factors. The other hydrogen is bonded to a bromine. Those 2 elements are in the same row. If you look at row 7a, you'll see fluorine, then chlorine, then bromine. That's 7a. On the periodic table, it's to the right of the periodic table. So the rule, if they're in the same column, is that for atoms in the same column, the hydrogen on an atom further down is more acidic. So this hydrogen here will be more acidic, and so you'd expect HBr to be more acidic. And the reason for that is, as you go down, the atoms become larger, and as the atoms become larger, there's more space for the atoms to stabilize a negative charge in. You can spread it out over more space so that it doesn't repel itself. It's more diluted, and so more stable, less intense of a charge in any one place. So the more acidic proton, the more acidic compound will be HBr for this. All right, next compound. We'll use the same 4 factors. Here, in the first molecule, the hydrogen is on an oxygen and water, and in the other molecule, the hydrogen is on a sulfur. So those are 2 different atoms, so we'll expect this first factor to be the decisive factor. And those 2 elements, oxygen and sulfur, are in the same column on the periodic table. Just below oxygen in group 6a is sulfur. So the rule for elements that are in the same column is that the hydrogen on the element that's further down, that hydrogen is more acidic. And that's because the atoms get larger, and so they can better accommodate a negative charge in them, spread it out, dilute it, make it more stable. And so H2S is going to be more acidic than H2O. All right. For C, first thing you want to consider is the atom. Now in C, the hydrogen is bonded to a nitrogen. For the first molecule, for the second one, the hydrogen is bonded to a carbon. So those 2 elements are in the same row. You have carbon, and right next to it, to the right, you have nitrogen. And the rule for atoms in the same row is that the hydrogen on an atom further to the right would be more acidic. That's what you'd expect. And again, these are just rules of thumb. There are definitely exceptions to them. These will sometimes lead you to predict something that is technically not true, but on the test you will be graded based on how well you followed these rules. And when you go through life and you're trying to assess the acidity of different molecules, you always want to take your assessment with a grain of salt, and remember to check it with pKa's and Ka's before you make any big decisions, because this is just a rule of thumb. So in that previous example, the NH3 is what we would predict to be the more acidic. For D, so here we have only 2 types of hydrogens. The blue hydrogen is on a carbon, and the red hydrogen is also on a carbon. So they're on the same type of atom, so that doesn't help us. If either of the types of hydrogens left, it would leave a lone pair with a negative charge on an atom with pi bonds. Neither of the lone pairs would be allylic, neither of them would be next to a positive charge, so there would be no resonance associated with either of those lone pairs that you would get after the hydrogens left with the electrons that were in the bonds to them. So resonance doesn't help us. Both of the molecules only have carbon and hydrogen, in other words, nothing especially acidic, and so nothing especially electronegative, and so induction doesn't help us out. So we're left down to the orbital. Now, in the molecule on the right, the carbons are involved in 1 pi bond. That means each carbon needs 1 of its p orbitals, and it only can use the other 2 to mix. So that molecule only has sp2 hybridized carbons in it. For the the molecule on the left, each of those carbons has 2 pi bonds. That means it's using 2 of its p orbitals. It only has 1 left to mix, so both of those carbons are sp hybridized. And the rule for orbitals is that sp hybridized carbons, hydrogens on those are the most acidic. And so here, the hydrogens that would be most acidic would be these, and this molecule as a whole would be more acidic than the molecule on the right. And that's because those orbitals, those sp orbitals, are holding the electrons closer to the nucleus than the sp2 orbitals, which hold them further from the nucleus, because these have more p character and the p is more linear, whereas the green ones have more s character and the s is spherical. Okay, if we go to E, so here are hydrogens. We have several hydrogens. Actually, we have 2 different types of hydrogens on both of the molecules. You have the hydrogen on the oxygen and the hydrogen on the carbon, and that's true for both of these. We've got hydrogen on oxygen and hydrogens on carbon. Now, we've seen before how carbon and oxygen are in the same row, row 2A, row 2, and oxygen is further to the right in that row. So the hydrogens on the oxygens are the more acidic ones. So those are the ones that we want to compare. So there's one of those in each of the molecules. Both those hydrogens are on oxygens, and so the atom is not going to help us to decide between those 2 circled hydrogens. Let me make one red so I can... They're blue and that red hydrogen. We can't tell which one's stronger there using the atom. They're both on oxygen. We don't have any pi bonds in either molecule, and we also don't have any positive charges. So the lone pair that would be left behind by the hydrogens when they leave, that is not going to be involved in resonance in either of the structures. So we have 0 resonance, so that doesn't help us. But what you'll notice is that we have more electronegative atoms in this molecule on the left, I should say. Those electronegative atoms take the negative charge that the hydrogen is going to leave behind and spreads it out over so many bonds. That same effect does not happen in the other molecule. There are no electronegative atoms funneling the negative charge their way. And so, the hydrogen that has the most electronegative atoms closest by, that hydrogen is the more acidic one. That's the molecule on the left. So that hydrogen, this hydrogen here, is the more acidic hydrogen, and this molecule is the more acidic molecule because it has that hydrogen on it. So that's another example of some molecules that you can use this REO for to assess their relative acidity qualitatively.